Okay, hello everyone. Welcome to the last keynote lecture session of School of Mathematical Psychology 2022. It's my pleasure to introduce our keynote speaker today, Professor Jörg Rieskamp. Jörg is a professor of economic psychology at the Faculty of Psychology of the University of Basel. In his research, he focuses on the development of cognitive theories of judgment and decision processes using computational cognitive modeling. So I can say his recent research topics cover sequential sampling models of decision making, reinforcement learning models of economic decisions, Bayesian models of strategy selection, and neural mechanisms underlying risky decisions. Okay, Jörg, thank you again for accepting the invitation. So please go ahead.
Thanks, Jamal. Thanks for inviting me. It's an honor to give a presentation here to this School of Mathematical Psychology. As Jamal already said, I'm running the group on economic psychology at the University of Basel, and we are very much interested in how people make decisions in an economic context. And we do this by exploring or by developing cognitive models or theories to explain why human behavior often doesn't follow the rules that the economists tell us. Yeah, so there's this homo economicus that economists often suggest, and then we see that people are not making completely rational decisions in line with this view. And our idea is to provide cognitive models to explain why these deviations are observed. As I said, usually I'm in Basel today, and the next 3 months I'm at the University of California in Irvine doing a sabbatical here. And I hope that my internet connection works properly so that you can follow me. All right. So this project, or I'm working on several projects, and they are all focusing on decision errors. At the beginning, when I started this project, I thought it's not, I didn't find it very interesting. I thought, well, it's not, is it really interesting to explore how people make mistakes? And I thought, well, maybe not. But then we continued this work and it became more and more interesting to me. And so I'm presenting 3 projects to you today. If I have time. I have so many slides, so maybe I have to skip the last one, but let's see how it goes. And I hope this is also interesting for you from a mathematical and cognitive perspective. But I will focus very much on decision making. So I will present also a lot of work on experiments, experiments on decision making. If you don't understand what I'm talking about, or if you have any questions, please interrupt me, and or you can also put questions in the chat. If I don't see you having a question, maybe Amir or someone could tell me so that I'll stop and try to explain things better. Okay, so now we get into decision making. All right. So, and the starting point is a Nobel Prize winner, Herbert Simon, who developed the concept of bounded rationality. Yeah, I already told you that we are interested in Basel in exploring why people don't make decisions following full principles of rationality. And one psychologist, Herbert Simon, he argued already, I don't know, this was 60 years ago when he did all this work, and saying, well, people make decisions that are not completely rational. And he developed this concept of bounded rationality. And he said, well, they make decisions with limited information, with limited cognitive resources, and with limited time. And in this project, we also explore what happens if people have less cognitive resources available, or if they have less time available when making decisions. And our idea is, well, if this happens, then they probably make more mistakes. And that's what we explore in this project. Okay. So how can we study the effect of cognitive capacity on people's preferences? Yeah. There are two ways how you can study this. The first way is to manipulate, to do a manipulation, experimental manipulation, like manipulating cognitive load to explore the effect on people's decisions. That's one way. Yeah. The other way is to follow a correlational design that relates cognitive capacity or abilities to decision-making preferences. So these are two routes how you can answer this question. Yeah. We will first focus on the first part, yeah, on experimental work that manipulates something or increases cognitive load to see whether this has any effect on people's decisions. Okay, so let's start with the manipulation of cognitive load. And I start with some work that I haven't done myself. Yeah, I just cite some other people's work now. And these people have explored what happens if you reduce people's cognitive capacities. Does that have any impact on people's preferences? Yeah? There are different preferences. We first look at social preferences or unfairness decisions. Yeah? This is just an example. And as I said, I'm citing here other people's work, and this work suggested that reduced cognitive capacities lead to more fair choices, so that people become more fair if their cognitive capacity is reduced. There are some ideas why this might happen, but I don't go into it, because other people couldn't find this effect and even argued for the opposite, that people become more selfish under when the cognitive capacities are reduced. Well, that's interesting. Yeah? So people have different views about this. But I show you one study that is by Schulz, Fischbacher, and others. And here they have a dictator game. I'm not sure. I mean, dictator game is one of the most famous games in experimental economics. Yeah, but I explained it to you because I heard that you worked about sequential sampling models, but maybe not about dictator games. So what is a dictator game? You have two players, two persons interacting with each other anonymously. Yeah. And the first player, I mean, you come into an experiment and then you're told you are the proposer in this dictator game, and you have to choose how to divide up a monetary resource. Yeah. So here are, for instance, $100, and you can divide them up either 50-50 or 80-20. Yeah. And this means that you as a proposer get either 50 or you get 80. And the second player in this game receives either 50 as you or only 20. So the fair split is, of course, 50-50. But the 80-20 is the unfair split, but which gives the proposer an advantage, and that's the selfish choice. Yeah. The responder in this game has no decision to make. He or she just gets the outcomes. Okay. So that's the game. Now the question is, what happens if people are under cognitive load? Yeah, and they use the n-bag task in this experiment. That means they saw these letters and they always had to remember the letter that they saw two times before the letter they recently saw. Yeah. And so they saw these letters, then they did the dictator game decision, and then they had to recall the letter. Yeah. And because they had to remember the letter at the same time when they made the dictator game decision, the argument is, okay, now you're under cognitive load. And the question is, does that mean that you become more fair? Yeah. So do people become more fair under high cognitive load? These are the results. Yeah. What you see here are the different splits, how they could divide the money, like 80-20, that's what I showed you. Or they could choose a fair outcome, 50-50. Yeah. So there were different splits, either 80-20 to 50-50 or 90-10 to 50-50 and so on. Okay. And what you see here is the percentage of fair choices. Fair means choosing the 50-50 split. The unfair split means to choose the 60-40 or the 90-10. Yeah. And indeed, if it's very unfair, 90-10, then the proportion of people who are choosing the 50-50 split is the largest. Yeah. And if it's not completely unfair, like 60-40, then more people choose the unfair split. What's interesting here is that what you can see, and that's in blue and red, in the control condition, people choose the selfish split more often than in the load condition. Yeah, on average, in the load condition, they choose the fair split in 34%. Sorry, I've said that wrong. 43%, right? So much higher than with 30% in the control condition. So we do see a big impact of the load condition. Yeah. So indeed, apparently, cognitive load leads to more fair decisions. So how do they see this effect? Well, they say, well, under low load, we observe 31% of fair choices on average, and under high load, we have an effect so that people choose the 43% more often the fair split, right? That's not my study, yeah? So I just give you a little introduction here. Okay, there are other people who have explored something that we are more interested in Basel, namely risk preferences. Okay, again, there are many studies that explore whether cognitive load has any effect on people's risk preferences, or whether people become more risk averse if they are under high load. And indeed, what they observe in this study, for instance, under low load, they observe 59% risky choices, and under high load, the participants choose the risky option only in 53% of the choices. Yeah. So apparently, again, we observe an effect of cognitive load. Here, people become more risk averse. Okay. I could go on to show you more studies on how cognitive load changes people's preferences, but I would like to indicate one problem. I don't know whether any one of you has already spotted this problem. The problem is the following. Okay, we had this 31% fair choices under low load, and under high load, we observed 43%. So what would happen if we had very high load? Yeah. Well, most likely, if the effect goes in the direction of having more fair choices, you would observe 50% fair choices and 50% selfish choices. Yeah. I mean, this is what you would predict. If the load increases, you should have an even stronger effect that people become more fair. Yeah. Okay. But now here's the problem. Hey, you could also observe this if people just flip a coin all the time. Yeah. If they are under high cognitive load, it could also be that you just flip a coin because, well, hey, it's really complicated to do all this at the same time. Yeah, doing this multitasking basically. And so maybe this has nothing to do at all with fairness preferences. Yeah. The only thing what we observe is that people make more errors. So instead of having, under low load, you observe 31% of fair choices. Well, and now we increase the cognitive load, and then they make more fair choices, but not because they become more fair, but just because they make more errors. Okay. I could stop here now because that's my message of this talk. Yeah. But since I haven't presented anything to you that I did on my own, maybe I should. Okay. And this also holds for the risk-taking domain, right? So we observe that people make less risky choices under cognitive load. But again, this could also be that people just make more errors. Again, we would argue that people's preference don't change under high cognitive load, but what's happening is that people just make more errors. And that's why I now find this project interesting. By exploring errors, we might identify that the conclusions that all these authors have drawn are, let's put it this way, problematic. Yeah, meaning, well, maybe there are no big shifts in preferences under cognitive load or other manipulations. Yeah, time pressure is another manipulation that have been used here, but it's just an increase of error. So we have now these two competing hypotheses. One, the other authors argued that there are shifts in preferences. We argue, no, this has nothing to do with preferences. It's just an increase of errors, or another way how you could say this is that there is a decrease in choice sensitivity. What do I mean with choice sensitivity? Well, I think you talked about sequential sampling models, right? So the decision threshold, that's the choice sensitivity. If you have a high decision threshold, it means that you have to accumulate a lot of evidence before you pass this threshold. If you lower this threshold, then you make a decision more quickly, and it implies that your choice sensitivity is lower. Yeah. So I have to admit, I mean, one could do this whole modeling with the sequential sampling model, but I'm not talking about it today. So please forgive me. Okay. We can talk about it at the end. I think one could also do this with sequential sampling models, and we will do so in the future. Okay, so our research hypothesis is, first of all, that cognitive capacity or ability is related to decision errors. And when you do some manipulation like cognitive load or time pressure, then this leads to more decision errors. That's what Herbert Simon told us, right? So neither cognitive ability nor cognitive load manipulation are related to people's risk preferences or their fairness preferences, or, and that's what I didn't show you, what we also explored, are people's time preferences. There are, as I said, many studies that explored how cognitive load changes people's preferences. And our bold argument here is that all this work is, well, should also take into account that people decision errors might increase. Okay. So we did our own studies, and I show you one study in which we explored people's risk preferences. And we did this following a cognitive modeling approach. And that's also how it relates to the topic of your school. So here is our task. And for those of you who are not familiar with decision-making experiments, this is how the experiment looked like for our participants. So here you have two choice options, right? And when you have to make these risky decision-making tasks, then people are often presented with two options. Here, these are two gambles, and one gamble is the safe gamble, and the other is the risky gamble, right? So if people are risk-loving, they will always choose the risky one. If they are risk-averse, they always choose, if they are very risk-averse, they always choose the safe option. So what is the safe option here? I'm not sure whether you see this immediately, but here, the right one, that's the safe one, because here you are guaranteed $50, yeah, $50 or whatever economic experiment accuracy. So that's guaranteed to you, and with a high probability you get even 75. Yeah. So if you are the risk-averse person, you probably choose that option. If you're risk-loving, you go with the left one. Why? Because here you have the opportunity to make 90. That's even more. But it's risky because the probability is lower. And if you're unlucky, you only end up with 35. Yeah. So that's up. There's no wrong or right decision. That's why we talk about preferences. It's your personal risk preference what you choose. Yeah. If you're extremely risk loving, you will choose the left option. But someone who is always playing safe, who is always going for the risk averse option, she will choose the right option, right? So that's why we always call this preferences, because there is no right solution to the problem. Yeah. This is also important if you look into the, I heard that you had Roger Radcliffe with you, and he's always talking about problems where there is a right solution. Yeah. And he always talks about accuracy of people's choices. But we are doing we are not doing this here because there is no right option. Yeah. So Amir could always choose the risky option, the right one, and Jamal might always choose the safe option, and there's nothing wrong about it. But what we explore is how often people choose the risky one in order to elicit people's risk preferences. Yeah. And now the question is, what happens if you have a load manipulation? We did a load manipulation here, a 3-back task in which you always had to remember the letter that you saw 3 times before. Yeah. And since you had to remember this, you were under high cognitive load, then you had to make your decision between the 2 gambles, and then you had to recall the letter. Yeah. And that's quite, I mean, it's quite complicated. If you do this yourself, you will figure out that's not so easy. Okay. They had to make 80 choices in 2 conditions, either with load or without load. And there was a 10 minutes break. Yeah. This is also a bit different to some of the experiments that I showed you, because we have a within subject design, not a between subject design. We had many choices. This allows us to characterize people's decision-making process more accurately, in our view, than some of the other studies. Okay. And they were also paid. Yeah. In the end, what we did, they always received a show-up payment, and then we selected one of their choices, so 1 gamble, and then we played the gamble, and according to the outcome, they received an additional money. Yeah. So that's why the payoffs that they receive varied substantially. Yeah. Okay. And here are the results. And maybe on the right side, you see the reaction time. People are slower under high cognitive load, which makes completely sense, right? So you have to remember this, and therefore it's more complicated, takes you more time. What we also observe is that people become slightly more risk-loving, but we don't have a big effect, to be honest. For that reason, what I show you here is we always had these pairs of gambles, and we computed the difference, the expected value difference between these 2 gambles. Yeah. So we computed the expected value of the risky option, and then we subtracted the expected value of the safe option. And then we grouped these 80 choices in 5 quantiles. And we had the first quantile as the one where the safe option offers better, higher expected value. And the 5th quantile is where the risky option offers you a much higher value. So in the 5th quantile, you should choose the risky option more often because it has a higher payoff on average. And on the 1st quantile, you must be very risk-loving to choose the risky option. So what you see here, when we look at the control condition, here in the 1st quantile, people choose the risky option not very often. And in the 5th quantile, when the risky option had a higher expected value, they choose it more often, like about 70% of the time, which shows us that people on average are risk averse, which is not surprising. But now you see this dotted line, and that's the load condition. And what we observe here, that in the 1st quantile, they choose the risky option more often, and in the 5th quantile, they choose it less often. But what we see here is basically it moves to the 50% line. Yeah. completely in line with our argument that under load, people make more errors. And that's why it moves to the 50% line. And in our experiment, because the gambles were sometimes offering the risky options offered sometimes more and sometimes less, we don't observe a strong effect on average, but we observe an effect if we look at these different groups of gambles. Okay. So basically, this is the descriptive results, but we like to identify or to specify the effect with a cognitive model. Yeah. And the model that we use here is this model that is very common in economics, and that's why we used it here. Yeah. As I said, one could also do the whole thing with a sequential sampling model, but in order to relate our work to the economists, we use this model that comes from economics. Yeah. And that's an expected utility model. I guess most of you have heard about it. Yeah. What do we do here? You compute the expected utility of an option, here of the first option A. And how do you do this? You take the sum of the utilities of the outcomes multiplied by the probabilities with which the outcomes occur. Yeah. So X might be $95. Then you take the utility of the $95 and you multiply this with the probability and take the sum over all outcomes that a gamble has. Yeah. Now the question is, what is the utility function? We use a power function, that is X to the power of beta. That's the utility function that we use. Okay. This is a commonly used utility function. So you see this, for instance, in prospect theory. Prospect theory, for those of you who don't know this, is the most famous descriptive model in developed by Kahneman and Tversky. Yeah. So this is the model that specifies the utility of the first option and the second option. And now we have to determine the choice probability. Yeah. And here we use the choice function. Yeah. So that's the easy part. So this is easier than if you use the sequential sampling model where you determine the choice probability due to this accumulation process. But here we use the so-called logit function, which is relatively easy. So you just take 1 divided by 1 plus e to the power of theta times the expected utility difference. So this is very standard. I guess you have heard about this. Yeah. Okay. All right. But there's one more parameter, that is theta, and that's the choice sensitivity. Yeah. And the larger theta is, the more sensitive you are. That is, you will always choose the with a higher expected utility. If theta is low, then you go, if it's 0, you will make random choices between A and B. Okay. That's great now, because this model is relatively simple and has 2 free parameters. One is beta up here, and the other one is theta. And the first one tells us about people's risk preferences. If beta is 1, they are risk neutral. They will make decisions in line with the expected value model. If beta is below 1, it means people become risk averse. The lower beta is, the more often they will choose the safe option. If above 1, they become risk loving. That is, they will always choose the risky option. Okay. So beta tells us what is their risk preferences, and theta tells us how choice sensitive they are, or in other words, how many errors they make. Okay. So that's cool. Why is it cool? Because now we can identify what really happens under high cognitive load. We have 2 parameters that tell us this. Okay. That's great. That's what we want to. And that's much better than just looking at 50%, 40% choices of the risky option. We have 2 parameters that tell us something about the setup of our participants. Yeah. And that's why I like cognitive modeling, because instead of just looking at the outcomes, the cognitive model tells us something about our participants and identifies something what we can call a cognitive construct, right? Okay. Yeah, this is what will happen. Yeah, if this illustrates the two potential effects of cognitive load. So here we have our model again. I showed this already to you. So there's too much information on this slide, but I showed you this already. Okay, this is the blue one. And now the question is, what happens if we have cognitive load? If we have a risk, and this line here, the blue line, shows you the choice probability of choosing the risky option or of choosing the safe option. And here we determine the expected value difference. Yeah. And what we see here is what happens if a cognitive load manipulation changes people's risk preferences. So if the parameter here of the utility function is increased, for instance, then we will see a move of people the curvature doesn't change, it just moved, so that people will choose the risky option more often. Yeah. Here down here, if we change the theta parameter, then the curvature changes. That is, people will become less sensitive of choosing the better option of the two. Okay. So this is how the model will change people's choice probabilities. Okay. And how did we estimate this model? We used the hierarchical Bayesian approach. I guess you have heard about it. So what does that mean? So we have these two parameters and we wanted to estimate them, and we used a hierarchical approach. That means that we have a distribution for both parameters on the group level for the whole population. Yeah, this is what we see here. So it follows a normal distribution with a specific variance. And this is what we want to estimate. So we want to figure out how these two parameters look at the population level, at the group level. But for each individual, we draw from this overall, from the highest distribution, we draw a distribution. Again, it's a normal distribution, and we estimate for each of the participants the mean of that distribution and the variance for both parameters, yeah, for this risk parameter and for the sensitivity parameter. Yeah, we call this beta 0 here and beta 1. So that, yeah, so the two parameters are in this model called beta 0 and beta 1. And this is our model again that we saw already before. I mean, here we have the beta 1, which presents people's risk preferences, and here we have beta 0 that presents people's choice sensitivity. Yeah, and in order to model this, we use this choice probability, and to put this into a Bernoulli distribution, this will generate all the choices. And now we will check, I mean, we estimate this model by comparing the choices with, I mean, the predicted choices with their real choices. Yeah, this is how this hierarchical model is estimated. Okay. And here are the results. And what you see here is the delta, that is whether there's any difference between the estimated parameter in the control condition and in the load condition. Okay. And this delta is, as you can see, well, follows the normal distribution and is basically centered around 0. So this shows us that this load manipulation seemed to have no effect on people's risk preferences, aligned with our hypothesis, but in contrast to all other people's work. But what we observe here is a shift in people's sensitivity, meaning that they become less sensitive in making their choices. Yeah. So this is the delta. Yeah. Remember, this is only the difference It's not the actual value of the parameter. But we observe a difference, and the difference tells us that people are more sensitive and choosing the option that they prefer. Yeah. Well, this slide is important, as this is basically the final the final outcome of our study. And here you see this. Yeah.
Sorry, this difference is control minus load, or load minus control? I didn't understand the sign of this is, for example, theta in control minus theta in load condition, or it's reverse?
So the theta is lower in the load condition, and the theta is higher in the control condition. So in order to have a positive difference, it means that we took the theta in the control condition minus the theta of the load condition. Yeah, and then it becomes positive, and that's what is shown here. Okay.
Okay, thank you.
So basically, people are more deterministic in the control condition. Yeah. All right. And here you see the means for the mean estimates for the participants. Yeah. So each point shows, each circle shows the mean estimate for the two parameters for the participants. And on the left side, we see the risk preferences, and we estimate those. I mean, you see this on the x-axis for the control condition, and on the y-axis for the load condition, and it's basically highly correlated with each other, but there's no shift. Yeah? So if it were, I mean, if they did this completely, if they did this exactly the same way, then everything should be on the diagonal. Yeah, but that's not the case. But nevertheless, there's no shift. But what we observe here for the choice sensitivity, that's very relatively clear here that there is a shift. So we have the parameter for the control condition, and we have the parameter for the load condition, and we observe a shift such that people are, or showing us that all people become less sensitive in the load condition. Yeah, and this is when we observe these parameter estimates. This is on the probit scale, so that's why these values are negative. Yeah, so don't be confused by the values that we see here. Now, they are not, they don't correspond to the theta value of the choice function. This is why, because we had to estimate this in the Bayesian way, and there we use the probit function, probit transformation. Okay. So let us summarize this. We are not saying that others did not find these shifts, yeah. And we have to admit that we did not do direct replication. So our experiment, our setup was different than the studies that other people have done. But nevertheless, we could not find these shifts and preferences in our experiments, yeah. What we find is that people just make more errors when you put them under cognitive load. And this is also indicated by this modeling enterprise that we took. Okay. So I hope you enjoyed this so far. Because now I'm coming to a second project. And that brings us to, or me, to the question of how we can estimate these choice models. Yeah, so I presented you this choice model, and I continue with it. And while we were doing this project, we thought, well, how good are we in estimating the parameters of our model? Yeah, so the question that came up during this project was, are we really good in estimating the model? So what we did a model recovery analysis, and we identified that the model that we estimated was accurate, yeah, or can be accurately estimated, given the experimental setup that we had. But we were not sure whether this always is possible, because we encountered a problem with that model that I showed you. Maybe someone has spotted this problem already. Excuse me, 1 second. Okay, let's come to this problem. Again, yeah, so we study these choices between gambles, yeah, and I already presented you 2 gambles, this time on the right side, or I think it was the same. Again, we have a safe gamble, and on the left side you have the risky one. Why is it risky? Because here you can make 85 dollars or experimental accuracy, that's what we call it here, but you have the risk that you end up only with 14. And on the right side, this is a safe option, because here you are guaranteed 24 and you can make 44 with a high probability. Okay, so again, this is how we do this, and everyone does it in this domain. And the utility model that I showed you worked. I mean, I present this model again to you. So we have the expected utility, yeah, of an option. And basically, when you use this logit function, it implies that you add an arrow to the utility. Yeah, and this arrow is IID. And if you use the logit function, it implies that the distribution that you have is an extreme value distribution. I guess I'm telling you nothing new. Not sure. Of course, you could also assume other distributions for this arrow, like the normal distribution. Why is this important? Depending on the distribution of the arrow that you add to the utility, you end up with different link function or choice function. This is the logit function that I already showed you. And this logit function implies that we implicitly assume that to each arrow, each utility, we add an arrow, epsilon, that follows a specific distribution. Yeah. This is the logit function. You could also use a norm. I mean, if you had a normally distributed arrow, then you need this probit link function. Yeah, that's more complicated. Why are people not using it? Because it has. Yeah.
Sorry, you're
end up with a different link function.
sorry, we did not have you for 10 seconds.
Ah, okay. Can you hear me now?
Yeah, yeah.
Okay, so maybe I repeat what I just said. So we have this utility function that I presented to you in the last project. And basically, we assume that there's an arrow always added to the utility. And the distribution of this arrow can be different. When one way or one assumption is that there's an extreme value distributed arrow. And if you have this assumption, then you end up with this logit function. Yeah. But you could also make the assumption that the arrow is normally distributed, and then you would end up with this probit function. Yeah. So in principle, you can have different assumptions about the arrow, and depending on which arrow assumption you have, there's a different way how you compute the choice probabilities. Yeah. Okay. And then there's another question, namely, how do you find utility? What I showed you is this power function. Do you remember I said x to the power of beta, I think. Here it's x to the power of alpha, but it's always the same. And that's this famous utility function that you find in prospect theory. economists also sometimes use this function that is called CRRA function. That's constant relative risk aversion function. That's also a power function. So it's quite similar to that power function, but has slight differences. Yeah. But now apply this, and I come to my question: how easy can you estimate the two parameters of this model? So let's say we have two lotteries or two gambles. Here you can make $200 with a probability of 50%, or otherwise you get nothing. And gamble Y is you get $100 with a probability of 1. So 100%. Meaning someone who's playing safe will always go for Y. Someone choosing the risky option goes for X, right? And let's assume we need to take this model here that I presented to you already a few times now. But now assume that we have two people. Yeah, I said Amir is the, what did I say? I don't know. The safe guy. Yeah, so, oh no, yeah, the safe guy. So alpha is 0.5 for Amir. Yeah. So if we now plug in 0.5 in our utility function and compute the difference of the utility, the expected utility of X and Y, we end up with the difference of minus 2.93. Okay. So now assume that Jamal is a risk-loving person. So he has an alpha of 2. So it's larger than 1, meaning this person is risk-loving. And again, I can compute the expected utility difference of the two options, X and Y. And in this case, it would be a difference of 10,000. Means this is nothing magic or so, right? But of course, depending on the parameters, you have a different difference. So now assume that both persons want to choose the preferred gamble with a constant probability, let's say 0.7, 70%. You choose either the safe option, or if you are risk loving, you choose the risky option. Yeah. So if you have an equal strength of preference, meaning that you choose the preferred option in 70% of the time, you need a different choice sensitivity parameter value. Otherwise, this will not work. Yeah. And now the interesting part is this value is completely different. So if you have the small difference with alpha of 0.5, you need a choice sensitivity parameter value of 0.29. Whereas if you had this alpha of 2 with this large, which corresponds to the large difference, you need a very small value for the theta parameter. So what did I show you? And actually, this is not my own. This is work that had already been shown by these former colleagues of mine. The conclusion is that the choice sensitivity cannot be interpreted independently of people's risk preferences. Yeah. So there is most likely a correlation between these two parameter values. So we wanted to show this, and therefore we did a model recovery. We generated 60 choices between two binary lotteries, and we used this model. And then we estimated the two parameters using a maximum likelihood approach that a lot of people do, right? And then we repeat this procedure 100 times. I think there's a question. Arash?
Yes. Could you please explain why we cannot interpret theta independently? Could you please repeat it? I didn't quite get it.
Yeah. Good question. Thank you. So let's say we observe these two values, yeah, and we had no clue about people's risk preference. Then we would say, well, this person, 0.29, has a much higher risk sensitivity. Yeah, this person is more deterministic in his or her choices, whereas the value of 0.000084 is a very small value. So we will most likely say, this person is not very choice sensitive. Yeah. That's what we usually, how we would usually interpret these values.
Yes.
But remember, those values lead to a choice or strength of preference for the preferred option of 70%. So the choice sensitivity is not really different. But why do we observe these different values? Well, that's a consequence of the very different alphas of the utility function. Yeah. So here we have these two alphas, and when you use these different alphas, you have very different expected utility differences, and that implies if you want to have the same choice sensitivity, you nevertheless need different choice sensitivity parameter values. Yeah.
Yes.
So depending on your alpha, it implies a different value for the theta parameter. And that makes the whole thing so complicated. These two parameters are correlated with each other. And therefore, when you look at just one value alone, if everyone has the same alpha, then it's okay. Yeah? If everyone has an alpha of 0.5 and you have different estimates for the sensitivity parameter, you can always interpret this. Yeah, because you can say, well, the risk preference is identical for all these people. The only difference that we see is the choice sensitivity that differs. Then you can have strong conclusions. But if you have people with different risk preferences, they will naturally have different choice sensitivity parameters due to the alpha value, and that makes the interpretation of the choice sensitivity parameter quite complicated. Yeah. This is a phenomena that you will have in a lot of cognitive models, by the way. This is if you have correlation between parameters, you will have problems in interpreting these parameters. Okay? So the model doesn't know anything about psychology, let's put it this way. And what I can do here, I can set one value up, the choice sensitivity, and then it will affect the other value, alpha. And it leads or can lead to same or similar choice probabilities prediction. And that's the problem that we have here. Yeah, I show you this with this model recovery. Maybe I go on. So here are the results. So we simulated this with two parameters for alpha, 0.8, risk-averse person, 1.2, excuse me, risk-loving person. And we said the error rate should be 20%, not 30% as I showed before, just 20%, meaning that the option with the higher expected utility will be chosen on average with a probability of 80%. In 20% of the cases, you make a mistake and you choose the option with the lower expected utility. Okay? In order to have this 20% error rate, you need different values for theta, for the choice sensitivity parameter, namely of 0.37 for when you have an alpha of 0.8 and of 0.05 lower value for the choice sensitivity if alpha is above 1, namely 1.2. Okay. Okay, now we generated this data and then we estimated alpha and theta, and these are the mean estimates. And as you can see, the mean estimate for alpha was relatively correct with 0.8 and 1.2. So similar to the alpha, to the data generating values. But for theta, we have a large deviation. The value was estimated to be much higher. 0.78 is much higher than 3.7, and 0.12 is higher than 0.05, right? But what we also observe, and that's what we said, a high correlation between these two parameter estimates, a negative correlation, meaning that if one value is higher, the other will be lower, and the other way around. Okay. And what's also interesting, this is this last line here, we checked an alpha of 0.8 means that the person is risk averse. Any value that is lower than 1 means the person is risk averse. Could it be that sometimes the estimate value of alpha is above 1? So you would conclude that the person is risk loving. indeed, that occurred in 36% of the cases. So here the estimate is really misleading, because you would say this person is risk-loving, but in fact, the person is risk-averse. And the same thing happens for the risk-loving person, even more often. In 50% of the cases, the estimated alpha was below 1, meaning that one would think the person is risk-averse. So we have a strong correlation, and we are relatively quite bad parameter recovery. Okay, now we thought, okay, can we solve this problem? Sticking to our model, but doing some manipulations. And I show you some manipulations that we did. Namely, we did some standardizations. Yeah. So since the parameter correlation stem from the scale of the utility difference, that's what I showed you at the beginning, that depends on people's risk preference, could we make the scale invariant? That was our question. Okay. So one way of doing a standardization would be to take the outcomes that we have in the gambles and always subtract the minimum mean outcome and divide this by the maximum of all outcomes and subtract the minimum mean outcome, and then the outcomes will always differ. They will always be on a scale between 0 and 1. And we thought by doing this, maybe this helps us to estimate the model. The second way would be, this is what you find in Basmeyer and Townsend's decision field theory. We use the utility difference, but we always divide it by the square root of the variance of the two utilities of the options. Yeah, they did this, and they also did this on purpose. I once talked to Jerome about it, that this helped them a bit to make their model better. And the last transformation, and that's something that our colleagues here suggested, namely Neil Stewart and Benjamin Scheibehenne and Thorsten Parfour, they said, well, maybe we use the utility function to determine the expected utility of the options, but then we retranslate this onto the monetary scale, yeah, so that we have not an utility of the option, but the monetary equivalent of the options. And maybe that's helpful to estimate the models. Okay. Well, here you see the results. This was the baseline condition of our model recovery enterprise. And here you see the 3 standardizations that you can do. And what you observe is that indeed it has an impact on the correlation. It becomes much smaller. And it also improves the recovery of the theta value. All 3 standardizations do this, but it does not change very much the recovery of the alpha parameter. So the essence, yes, it's helpful, but it's not a perfect solution. So then the estimate of the parameters. Well, we gave participants here 60 choices, and we thought maybe it's helpful if we increase this to 600 choices. I mean, we can easily do this in a simulation, right? So therefore we thought, well, what happens if you increase the number, I mean, the magnitude of the data that you have? And indeed, it increases or improves the estimate of the 2 parameters. So those parameters are much better estimated now if you have much more data. Well, that's maybe not too surprising, but so if you ever do an experiment and if you ever work with a model, it's very helpful if you have more data to estimate your models. Interestingly, this does not affect the correlation. The correlation goes even up. So there is a correlation between these 2 parameters. But now, since the estimates are quite accurate, we don't care so much about this correlation anymore. Yeah. And of course, 600 choices is something that is really high that you cannot do in a real experiment. So the question is, you need to make a trade-off, and you have to, when you do an experiment, it might be helpful to do a model recovery first to figure out how many choices do you really need to have a good estimate of your model. Okay. Another way, what you could do is to maybe to increase the incentive for your participants, or to give them more time, yeah, so that they really make good choices. So maybe you find a manipulation that increases people's choice accuracy. So instead of having 20% of errors, what happens if you have a manipulation that increases people's accuracy so that the error rate is only 20%? Well, is that, if you can find such a manipulation, that would be good, because here again, what we observe are that the estimates become more accurate. Yeah. So both ways can also improve the estimates of the model. Yeah. There's another way, is to use a so-called adaptive design. So people make some choices and then you change the choices that they make depending on their choices. This also helps. I don't go into the details of this because I'm running out of time. I just want to conclude for this project that these standardizations that we suggest can decrease the correlation and do improve the estimate of the choice sensitivity, but they do not improve the recovery of the risk preference parameter. In order to improve both parameters, what you also need is to have a larger data set, or having more choices, and try to decrease participants' choice errors. If you are successful with that, then you can also improve the estimate of the model. And the adaptive design, that's what I didn't show you now in detail, can also improve the recovery of the risk preference parameter, but only slightly. So basically what we have seen here is that there are different techniques. They help to estimate the model. One should use them, but they are not perfect solutions. But so the interesting part of this project is to become aware of this problem. And this is also something that you might also be important in other projects when you work with other models, because these parameter correlations might also occur. Okay, so now I give you, I have 2 more minutes maybe. So I give you a very quick intro, very quick overview of the last project. Here we did a meta-analysis relating cognitive capacity with risk-taking behavior. Yeah, so I told you in the very beginning, an alternative approach is just to have a correlational technique to see whether cognitive ability is related to risk preferences. And there are many studies who have done this, and therefore we did a meta-analysis analyzing those studies. And again, we used the Bayesian approach, a very simple model, a random intercept-only multi-level model using Bayesian methods. And we also explored different moderators, whether they affect the correlation between cognitive ability and risk preferences. And as I said, I don't have much time, so therefore I go through this very quickly. But here you find the results of all these studies that we analyzed. And here you see the Fisher set transform correlation coefficient between cognitive ability and risk preferences. And as you can see, on average, we don't find a correlation. There is no correlation between cognitive ability and people's risk preferences, as we argued at the very beginning. But you do find some variance. Yeah, so some studies found a positive correlation, and most, I mean, the larger number of studies found a negative correlation. There are also a lot of studies that didn't find anything, but it's important to say, well, there is some heterogeneity, and some studies found the correlations, others did not. Okay, on average, you don't find any correlation. Now, but now the interesting part is, why did some studies observe a correlation and others a positive and others a negative one? And let's take one study here, the study by Doman. So this is on average, we don't find adequate correlation. Yeah? And we want to explain this. And this is a study by Doman. And this is how they explored people's risk preferences. They gave them this so-called multiple price list. And what you can see here is you are either given this sure payment of $10, $20, $30 for sure, or you have to choose a gamble. And the gamble means that you can make $300 or you have nothing with a 50% probability. And the task that you have here is to decide at what point, at the beginning, when you get nothing, for sure, you prefer the gamble, right? But at some point, the sure payoff gets always larger. And at some point, you would switch. But what's interesting about this design, and you find this in many, many of these experiments, when they use the multiple price list, you have the expected value for both options is not in the middle of this list, but is biased. Yeah. So here, at choice or decision number 16, you have $150 for sure, and this is exactly the expected value of the gamble. So you have many more choices where the expected value of the risky option is larger than the sure payment. And why is that? Why do you observe this? Why is it not symmetrical? Okay, that's the answer is that most people are risk averse. Most people are not risk loving, and therefore they have, most of these authors use more choice options where the expected value of the gamble is higher, in order to have a higher resolution to characterize people's risk aversion. So there's a good reason for it, but nevertheless it has a problem. And the problem is, again, our random choice behavior. If people make these choices randomly, what will happen? Well, they will end up choosing the safe option more often than the risky one, because they are basically, they will, let's say if someone who makes these choices completely randomly will choose 10 times the safe option and 10 times the risky option. If people do this, the authors will conclude that this person is relatively risk averse. A risk neutral person should choose the safe option in 60 times and the safe option only in 4 times of the cases, right? Now that's interesting. So now imagine someone with low cognitive abilities, this person will make more errors. And if this person makes more errors, it implies that this person will be classified as being risk averse in this task. So that's funny. So the authors will say, well, there is a correlation between cognitive abilities and people's risk preference, but that's not the case. It might only be that the person makes more errors. And so what we actually have is a correlation between people's cognitive abilities and their risk preferences, and their cognitive abilities and their errors, or the errors that they make, but not with their risk preferences. And we analyze this in this study in order to check what is the proportion of choice option where the expected value of the safe option is larger than the expected value of the risky option. And what you observe here, and that's what you would expect, is that you then observe that the correlation between cognitive abilities and the risk preference is negatively correlated. And that's what we show here. This is this moderator of this bias of the multiple price list. And indeed, what we see here is that this affects the correlation. Yeah. So in the study by Doman, they found a negative correlation because they had so many choice options where the safe option was better than had a lower expected value than the risky option. Okay, so I should come to an end now. So this meta-analysis showed us overall no credible correlation. And we also explore different moderators. I'm not going into this. The overall correlation is all altered whenever the risk elicitation method is affected by random errors. Yeah. Okay, let me come to a final conclusion. Cognitive load did not credibly change people's preferences, but decreased people's choice sensitivity. And we showed this in different experiments. The one that I showed you was on risky choices. So people's behavior is strongly influenced by decision errors, which could be misinterpreted as a decision preference. And when the risk preference parameter is estimated and the choice sensitivity, this can be problematic or complicated due to the correlation of both parameters in some models that I showed you. And I also showed you at the very end that the meta-analysis shows us that that how risk preferences are measured also have an effect on the observed findings. Okay, with that, I'm coming to the end. These are the people with whom I have done this work. And these are the papers in which this is all presented. Okay, I should conclude. I'm over the time, sorry.
Great, Jörg, thank you for your nice presentation. It was very interesting. Everyone, any questions? Yeah, Arash.
First of all, thank you for your presentation. It was really nice. About something I have read in some of the linguistic papers, they wanted to investigate the effect of second language second language effect on decision making, and they have similar context as you showed here. They wanted to check that if risk aversion changes with second language accusation, and they have two potential reasons for this effect. Second language makes us less risk averse. We tend to make more risks, and they actually said cognitive load and emotional component has this effect, are the reason for this effect. They didn't do any modeling. They just do some experiments, and their experiment was exactly like what you say here: dictator games, Asian disease, or something like this. On those papers, whenever the emotional component was decreased, for example, Asian disease, and in an alternative for Asian disease, they use some money to decrease the emotional effect. And in that case, maybe cognitive load had some effect. What I want to ask is, can we model this interaction between emotional effect and cognitive load with these models, or we can't? I mean, somehow we relate the emotional effect to alpha parameter, and as we see cognitive load to theta, or we cannot do that because the correlation you said about it.
Thanks, Arash, for this interesting question. So can you hear me?
Yeah.
Yeah? Sorry if the connection is not
Just
perfect.
Disconnected. We disconnected at the same time. Sorry, go on.
Okay, so this is an important point, and so I did not completely understand the experimental design of the experiments that you suggested, but you are right. There are other studies in which one did a manipulation, like emotional manipulation, and argued that this has an effect on people's preferences. And indeed, what we have shown can be shown for a lot of different areas. If the experimenters does not control our behavior, they might misinterpret the results as an effect on people's preferences. Yeah. So let's say, I don't know whether I've just imagined such a study where you give people a task in English and they are either native Americans or learned this, or this is their second language, like mine, right? My first language is also different. And well, it's a between subject design. You can't do anything about that, right? So you have one group, native English speakers, and the other group, non-native English speakers. And now you observe that people where English is a second language make, for instance, more risk-averse choices. I mean, you could come up with a nice story behind it. Yeah, you say, well, you know, you're not so sure about what you have read, and you don't understand whether what you do here. Exactly. So you become more risk-averse. So it would make completely sense that people who where English is not their first language, might become more risk-averse. Yeah, and then you have this interpretation. People running around with their second language, they are more risk-averse than the native English speakers. But that would be an incorrect conclusion, because the only thing what we might observe is that not people become more risk-averse, but that people just make more errors.
Exactly.
Yeah? And this is, and so if you can, so I talked with Sebastian Olszewski, he's one of my co-authors. And we thought, hey, we could go on with this project forever, because we could go on with all these experiments in which psychologists did not explore or did not control for error. Yeah, you will not find this, by the way, in Roger Wagler's work, and because he is so aware of errors, right? So a lot of cognitive modelers, when I present this work to them, they say, yeah, of course you have to take errors into account. Yeah, but if you look into these studies on social preferences of these economists, there's no word about the error interpretation. Yeah, so it depends a bit. Yeah, but I could imagine, I have to admit, I don't know this work on language acquisition, right? But I could imagine that people do it or couldn't have the, I don't want to attack them, right? So how do I say this? So people might not be aware of this problem. Yeah. So they do a nice experimental study where they have this between subject group, these people where English is a native language, people where this is a second language, and then they explore the differences, and they might observe different preferences. But again, it could be that it's not a shift in preferences, but it's just an increase of error. And we are just arguing, when you do such experiments, you need to take into account that the material that you are using might lead to a shift when people make more errors. Yeah. Okay, that's what I wanted to say. Long answer.
Thank you. It was very nice, and I think yes. In those papers I read and with your talk, I think yes, that is something like this model and this kind of interpretation is needed there, with my knowledge at least. Thank you very much.
You're welcome.
Okay. Amir?
Thank you very much for your nice presentation. I have two questions. One general question and one specific question. My technical question is that change the sampler algorithm for your Bayesian estimation procedure or not, and which sampler did you use? Because maybe the problem will solve by changing the sampling algorithm, the MCMC sampling algorithm. Because recently, for example, Scott Brown and some of his colleagues showed that using different sampling algorithms can be improved the recovery parameter for LBA.
I think, thanks Amir for the question. I think we use the Metropolis sampling algorithm. And I have to admit that you might be right that this could also affect the results if you use a different sampling algorithm. But as you have seen, the correlations were really huge between the parameters. And so you are right that if you had or if you improve the estimation process, the results might also become more accurate. But in principle, as I showed at the very beginning of this talk, it's a fact that there is this correlation. And I can show you that I can almost, I mean, with different parameters, yeah, if I move up one parameter and move down the other one, I will see very similar choice probabilities. And that's a fact of this model, that you can't really get away with a better estimation process. You're right. I mean, if the estimation process is improved, yeah. So in the second project, we only relied on maximum likelihood estimation. So that's not a very, I mean, the Bayesian estimation would be much better, which I used in the first project. And there we used the Metropolis sampler. So you're right, the way how we estimate the models has an impact. And the better, I mean, the more, if you have an improved way of estimating the model, you become also, your results will become more accurate. But nevertheless, you will still end up with the same problem due to this correlation between the parameters. So yes and no. On the one hand, you're right. It's always good to improve our methods, and you will get better estimates, but you will, in our case, will not get around the whole problem. Okay, thank you.
Thank you. Thank you very much. And my modeling in the different trends in this context, for example, using quantum models, using some economical models, and using some sequential sampling models are different trends in this context. But what do you think about the future, and what will remain in this context?
So that's a good question. And I think you also have worked, and we have worked on sequential sampling models, for instance. And I do think these models are cognitive more plausible, and therefore I would also apply them. Nevertheless, I mean, so the models we have worked with are much more complicated. They are not having these two parameters. They're having many parameters. But now, I mean, we put a lot of effort into this model recovery and doing some manipulation to find out how good these two parameters can be estimated. Now, let's say you have a model, the ones that you are working with, Amir, like have 6 or 8 parameters. Well, now, if you have such complicated models, it becomes much more complicated to detect these problems or specific correlations between the parameters. So on the one hand, these complex models are good because they can characterize more different cognitive processes, and therefore I also like them. But we have to be aware that when we interpret these models, we should be very careful, because before we haven't really analyzed the model in all details, we might overlook some of the parameter correlations that can also occur in these more complicated models. And because they are so complicated, we don't go into the details of these specific problems, right? but that is the danger, because then we might end up with interpretations that are not really robust. And that's one of the problems that you face when you have these more complicated models. So one should be aware of this problem, that the more complex the models become, the more time you should invest, how good you can estimate them.
Yeah, thank you. And thanks again for your nice presentation. The design was very interesting, and I just enjoyed your presentation. Thank you.
Yeah, thanks for inviting me. It was a pleasure presenting some of our work to us, and yeah, hope we will run into each other in the future.
Thank you. Thank you. It was our pleasure to meet you in this mathematical psychology school.
Great.
Thank you. Bye.
Bye-bye. Take care.